Welcome back, students. In the last sessions, we have overviewed on various concepts in gaseous state such as postulates of kinetic gas theory, kinetic gas equation, derivation of real gases from ideal behavior, and van der Waals equation of state for real gases. In this lecture, I will be discussing on the concept known as Maxwell's distribution of molecular velocities and energies. The Maxwell's distribution of velocities essentially gives us the most probable distribution of speeds of gas molecules in a gaseous system. We know that by kinetic theory of gas molecules are constantly moving in all directions, and during their motion they collide with one another and also with the walls of the container. And during these collisions there will be an interchange of momentum, and this interchange of momentum will result in the change of velocity of both molecules involved in the collision. A change in velocity means a change in energy. So, this also means that the collisions causes an interchange of energy between molecules. The total energy of the system may remain same constant, but the energy of the individual molecule will be continuously changing. Thus, all molecules present in a given sample of a gas do not possess the same speed. Okay, you can see over here, we have a closed container, and in this container we have n number of gas molecules. Okay, and if we examine the speed of different gas molecules in this gaseous system, we could see that the speeds of individual molecules are different and distributed over a wide range. Okay, and the speeds of different molecules goes on changing. Okay, if you observe any of this red colored gas molecule, you could identify that after each collisions its speeds are changing. Okay. And however, the distribution of speed among different molecules remains the same at a particular temperature, although the individual speeds of the molecules may change. The distribution of molecules between different possible speeds was given by Maxwell and Boltzmann utilizing probability considerations. Okay. What Maxwell and Boltzmann have done is that they plotted the fraction of molecules or the number of molecules along y-axis, and it is plotted against velocity in the x-axis. Okay. So, a plot or a curve is obtained by plotting so, and this figure is known as Maxwell's distribution curve. And the important features that we understand from Maxwell's distribution curve is that the fraction of molecules with very low and very high speed is very small. That is, you can see that towards this left hand and right hand, the number of fractions is so small. That means that the number of fractions with very high speed and very low speed is very small. Okay. And the fraction of molecules possessing higher and higher speeds goes on increasing till it reaches a peak, and then it starts decreasing, and the maximum fraction of molecules possessed a speed correspond to the peak in the curve, and this peak in the curve is called most probable velocity. And if we analyze the mathematical representation of Maxwell's distribution of velocities, the equation is such that it is P of C dc is equal to 4 pi m divided by 2 pi kt raised to 3 by 2 c square e raised to minus mc square divided by kt into dc. Here P of C dc means the probability of a gas molecule to have a speed between c and a small difference dc, that is c and c plus dc, and k here means Boltzmann constant, T is temperature in Kelvin, and pi you know it is a constant which value is 3.14. Okay. And this equation also means that Maxwell's distribution of speeds of gas molecule is directly related to the temperature in Kelvin and molar mass of a gas, and this equation is also known as Maxwell-Boltzmann distribution law. Okay. So, now we shall look on how this equation is derived. Okay. Let us first consider a gas molecule, and this gas molecule is able to freely go through all the three dimensions, but at first we will consider only the movement of gas molecules in the x-axis. And you can see over this figure that u is the velocity component along x-axis, W is the velocity component along y axis and V is the velocity component along z axis. Okay. And if you are considering the x axis, movement of the gas molecule along x axis only, then we can write kinetic energy will be half mu square. Okay. And according to Boltzmann, the probability of a molecule having energy E is proportional to E raised to minus E by kT, that we know actually. Okay. And here K is Boltzmann constant and T is temperature. Now, if you are looking at the probability of this particular gas molecule to have its velocity component between u and u plus du, that is we are focusing on the velocity u and its small difference du. So, the probability of that gas molecule to have this velocity between u and du will be then proportional to this according to this Boltzmann relation, that is P of u du is proportional to E raised to minus E by kT, which is equal to or which is proportional to E raised to minus mu square divided by 2 kT. Here we have E replaced E with mu square because E is kinetic energy of the gas molecule. Okay. And in order to remove this proportionality sign, we have introduced the proportionality constant A to our equation, that is we get P of u du is equal to A E raised to minus mu square divided by 2 kT into du. Okay. And now our next focus is to remove this or to understand what is the value of this proportionality constant A. Okay. For that, what we assume is that we apply the condition that total probability is unity for this case. Okay. That is over the integral minus infinity to infinity P of u du is equal to, we are applying the integral to the both sides of our equation, so that the other side we get A, because A is taken outside the integral because it is a constant, and integral minus infinity to infinity E raised to minus mu square by 2 kT du, and this we equate equal to 1 because we have assumed a condition, that is our probability is unity. Okay. And you might have already studied in your lower classes that the integral minus infinity to infinity E raised to minus bx square dx has a value that is root of pi by b. And here when we are comparing this with our condition, we have b is equal to m divided by 2 kT. So, we are applying this equation to ours, and what we have is that means this part we are finding the value, and we have A integral minus infinity to infinity E raised to minus mu square divided by 2 kT du is equal to A, and this part we are applying this equation to get pi divided by m divided by 2 kT raised to 1 by 2, which is equal to 1, and from this we can easily now estimate what is the value of A. Okay, that is we are just rearranging, we get A into 2 pi kT by m raised to the power 1 by 2, which is equal to 1, that is A equal to m divided by 2 pi kT raised to 1 by 2, and this is this value now we substitute into our previous equation, so that we get the Maxwell distribution of molecular velocity for the gas molecule in one dimension. Okay, that is P of u du is equal to m divided by 2 pi kT raised to 1 by 2 E raised to minus mu square divided by 2 kT du. Okay, as I said, this is a case for gas molecule along component u only. Now we have to consider the gas molecule movement or in all the 3 dimensions. Okay. So, for that we consider P of u v w du dv dw, which is equal to we modify our equation like we introduce all the 3 components to our equation, that is m divided by 2 pi kT raised to 3 by 2 E raised to minus m u square plus v square plus w square divided by 2 kT into du dv dw. Now, if you are considering a case, for example, I am considering this gas molecule, and if it has the velocity points, that means it can travel to this distance and be like here or around here, because we are considering the 3 dimension. Okay. So, I am considering the velocity points over a circle with the radius r, that is the radius is r, and its thickness of this sphere, it will be equal to dc. Okay. And now if I am considering the velocity points like this, I can modify, that is I can take the value du dv dw which is equal to 4 pi c square. Okay, so I am introducing that into my equation, that is this equation, so that I can modify the equation and write it as P of C dc is equal to 4 pi m divided by 2 pi kt raised to 3 by 2 e raised to minus mc square. I have replaced u square, v square, w square with c square because we are now considering the velocity in all the 3 dimensions. Okay. So, it is e raised to minus mc square divided by 2 kt into c square dc, and this is the Maxwell distribution of molecular velocities. Okay. Now, actually this equation can be stated in 3 different forms also. Here I have represented the equation in terms of probability. In the next step, I am representing it with relation to the fraction of molecules with a particular velocity, that is dn by dn is actually the fraction of molecules with a particular velocity c, and that can be written as 4 pi. Now, here if you look m means the mass of the gas molecule. Okay. Now, I am considering the whole system, so that I am replacing m with molar mass divided by Avogadro number. Okay. So, I am replacing that m and modify the equation, that is we get 4 pi m divided by 2 pi Na kt raised to 3 by 2 e raised to minus mc square divided by 2 Na kt c square dc. As I said, m is the molar mass and Na is the Avogadro number. And also we know that Avogadro number into Boltzmann constant k, which is equal to real gas constant. So, I can replace now with this Nak and over here also with r, and get dn by n equal to 4 pi m divided by 2 pi rt raised to 3 by 2 e raised to minus mc square divided by 2 rt into c square dc. Actually, this 5, 6 and 7 are the different forms of Maxwell's distribution, that is different forms, mathematical forms of Maxwell's distribution of velocities for a gaseous system. Now, we shall look on to the graphical representation of Maxwell's distribution. Actually, I have shown you this graph previously, and the most important features of this graph, as I discussed earlier, is that the probability of a molecule being motionless is almost 0. That is, we could see that from the origin itself the graph is starting. That means that velocity v or c equal to 0, the fraction of molecule is 0. That means the probability of a molecule being motionless is almost 0. Okay. And for velocities greater than 0, the probability increases with velocity, passes through a maximum, and then it falls away towards 0. Both very low and very high velocities are highly improbable. That is, fraction of molecules having very low and very high velocities is very small. And also we get the information that the area under this peak, if we calculate or integrate the area under the peak, we get the total number of gas molecules which is under study. Okay. And the probability of molecules having velocities which are neither very low or very high is very large. That is, fraction of molecules having velocities which are neither very low nor very high is large. Okay. And the peak of the curve corresponds to the velocities which is possessed by maximum fraction of gas molecules, and it is called the most probable velocity. Okay. So, most probable velocity is actually the peak of the curve, and it is also important to note that the molecular distribution of velocities at a given temperature does not change with time and under the same defined condition, and this is because during collisions molecules having particular velocity get interchanged, but their average number remains the same. Okay. And also the other information we get from this graph is that the arithmetic mean of different velocities of all molecule is average velocity. That is, we are finding the sum of different fractions of molecules with different velocities, and we are finding the sum of it, that is average of it, and what we get is the arithmetic mean of different velocities, that is average velocity. And also another velocity value that we get from this graph is RMS velocity, that is the square root of the mean of squares of different velocities. Actually, I will come to these sections in the next session. Okay, more detailed class will be given later. Anyway, these are the most 3 important velocities that we can obtain from this graph. Okay, and from the graph it is also clear that the RMS velocity will be greater than average velocity, which will be greater than most probable velocity. So, now you might think that why this average velocity is not itself the most probable velocity. Okay. Now, we will look the effect of temperature on Maxwell's distribution of velocities. From the mathematical representation of the Maxwell's distribution of velocities itself, we can see that the fraction of molecules is inversely proportional to the temperature. That itself says that as the temperature increases, the fraction of molecules with a particular velocity will decrease. Okay. That is, on plotting probability versus velocity at different temperatures, it is clear from this curve. That is, here I have shown the examples of the curves at different temperature ranges, ranging from 1000 Kelvin to almost 1000 Kelvin to almost 100 Kelvin. Okay. And as you can see over here, as the temperature increases, the peak of the curve shifts towards the right, isn't it? That is, the most probable velocity is shifting to the right as the temperature is increasing. Okay. And the peak of the curves are flattened as the temperature is also increasing. At 1000 Kelvin, it is more flattened when compared to that of the 100 Kelvin. And at lower temperature, molecules have less energy and hence the distribution is smaller range. And as the temperature increases, the fraction of molecules having higher velocities increases and the velocity distribution becomes broad. And the fraction of molecules possessing the most probable velocity decreases as the temperature increases. Okay. Here I have shown 2 different fractions, that is F1 and F2 for temperature 100 Kelvin and 200 Kelvin. And here it is clear that for 100 Kelvin, this fraction F1 is having a much higher value than for the case of the temperature with 200 Kelvin, which is F2, that is having a much lower value than F1. So, as temperature increases, that is T1 is greater than T2, this F1 is, T1 is less than T2, this F1 is greater than F2. Okay, that is the information that we get from Maxwell's distribution curve on its effect on temperature. Okay. Now, we shall look the effect of mass on Maxwell's distribution of molecular velocities or the curve. Okay, here I have shown the examples of different noble gases with different masses. Okay, here it is xenon, argon, neon and helium, and as you can see that as from left to right, this masses is actually becoming smaller and smaller. Okay. So, on average, heavier molecules move more slowly than lighter molecules, isn't it? Therefore, heavier molecules will have a smaller speed distribution while lighter molecules will have a speed distribution that is more spread out. Okay. And that is what seen here for xenon. It is a heavier molecule, so it will have a distribution curve which is much narrower. But as you go from argon, neon and helium, for the case of helium, it is a very light molecule when compared with the other 3. And so, its velocities will range broadly and hence this Maxwell distribution curve is of broad. Okay, that means that as the mass increases, the fraction of molecules having higher velocities decreases and the velocity distribution becomes narrow. Okay. Now, we shall move on to the experimental verification of Maxwell's distribution of velocities. Here an good example is the Stern's experiment developed by the scientist Stern. Okay. Here, now consider an electric oven which is filled with cesium atoms, that is, it is filled with cesium molecules, gas molecules, and there is an opening towards the right of this electric oven, and this opening is, and after that oven there is a slit, and the openings of the oven and the slit is in a straight line. Okay. And before that a tungsten filament is kept, heated tungsten filament is kept. Okay. And here this heated tungsten filament is heated at some higher temperatures. Okay. So, this cesium atom is actually those cesium atoms, actually this cesium atom can move because they are gas molecules, they can move in all the 3 dimensions, and those cesium atom which is coming to through this opening, and if it is an horizontal way, it can go to through this slit and reach the filament and strike the filament D, isn't it? Okay. So, but this happens only if you consider that there is no gravitational field. Okay, but this is not actually the case. We have gravitational field by nature, and so if a cesium atom is coming in horizontal way, it will go and strike to the lower side of the slit, and it will be it will not go further to the heated tungsten filament. Okay, but if this cesium atom is having a Y component, that is though cesium atom is coming through that slit or through this opening has a Y component, it can take a trajectory like this and it can go and strike over this heated filament at D dash. Okay. And if it has a more Y component than this, it again can go and strike over D double dash. Okay. So, what we understand from this is that the particle 2, I name this as particle 1 and this as the particle motion of particle 2 and this as particle 3. So, what we understand is that the particle 3 has more velocity than particle 2. Okay. And suppose u is the x component velocity and v as the y component velocity, then c square is the root of u square plus v square, and for particle 2 v is lower than in the actual scenario. Okay. And hence the particle 3 has higher velocity. So, what we can conclude over here is that lesser the velocity particle will hit the point near D, greater the velocity it will point near D double dash. Okay. And the distance from the D is proportional to the velocity of the particle, that is how we can map the velocity of the particle in relation to its distance. Okay. And now as soon as the atom gets hit on the tungsten wire, it becomes ionized, and once this atom is ionized, it will be collected by a detector which produces the ion current, and this current is directly proportional to the number of ions reaching the detector. More the number of particles hitting on the filament, more will be the ion current. So, after performing the experiment, we plot the intensity of ion current against distance, and the plot looks somewhat like this, and this can be related to the Maxwell distribution of velocities. So, what we can conclude over here that the density is proportional to the intensity, that means how many strikes we are receiving in this tungsten filament, that means that particular strikes have gas molecules with that particular velocity. So, the intensity in the peak corresponds to density, and that relates the velocity of the gas molecule, and the distance proportional to D, that is if it is near D it will have a smaller velocity, and to D dash it will have a greater velocity. So, that means distance is proportional to velocity, and this is the experimental verification for Maxwell's distribution of molecular velocities. Okay. And another example is that we shall discuss the concept of Doppler effect, how it is broadening the spectral lines on the basis of Maxwell's distribution of molecular velocities. Actually, Doppler effect, you might be knowing, it is the increase in frequency of waves as the source and the observer move towards each other. Okay, here you can see the equation, that is F equal to F0 into V1 or plus or minus V by C. Here V is the velocity with which the observer is moving to the source or vice versa, and C is the speed of the light. Okay, and F0 is the initial frequency and F is the final frequency. Okay. So, based on this Doppler effect, Doppler broadening is happening, and this Doppler broadening is actually the broadening of spectral lines due to the Doppler effect caused by a distribution of velocities of atoms or molecules. Now, if you are going to some experiments with gas or gaseous mixtures, and for the time being all atoms are at the rest, then we will get sharp lines in the atomic spectrum, but this is not actual case and it is not true. According to Maxwell-Boltzmann distribution, we have the molecules with all sorts of velocity ranging from 0 to infinity that you have seen earlier, right. So, some moving to you or some away from you, okay. And according to the Doppler effect, if the source is moving towards you, the frequency will increase, and if it is moving away, the frequency will decrease, right. Here, the atom is the source and is undergone radiation, absorbs the energy, and excited atom emits the radiation at a particular frequency during de-excitation. Since atoms are moving away and towards, that will result in a cumulative effect, and this finally leads to the broadening of atomic spectra instead of giving sharp lines, as you can see over this figure. Okay. So, that is another example of Maxwell's distribution of velocity. That is the reason behind the Doppler broadening in spectral lines. Okay. Now, we will move to the Maxwell distribution of molecular kinetic energies, how the kinetic energy is varying for different gas molecules in a system. We know that kinetic energy is equal to half mc square, which can be rearranged to get c square is equal to 2E by m. And that is differentiating with respect to c, we can write it as 2c into dc is equal to 2 by m dE, okay, or c into dc is equal to dE by m. That is, substituting these values, c square dc is equal to c dE by m, we can get the equation as 2E by m raised to the power half dE by m, which is equal to root 2E divided by m 3 by 2 dE. Okay. And now we are substituting this relation, that is c square dc term we have in our Maxwell distribution of velocities. So, instead of velocities, we are substituting it with in terms of the energy terms. Okay. So, we are substituting in our Maxwell relation as we know it is of the form like shown here, and to this we are substituting instead of c square into dc, and what we get is p of c dc is equal to, in terms of fraction, dne by n, that is dne by n means the fraction of molecules having a particular kinetic energy E and E plus within E and E plus dE. Okay, that is equal to 4 pi m divided by 2 pi kt raised to the power 3 by 2 E raised to minus E by kt into root 2 E by m raised to 3 by 2 dE. Okay, that we can finally rearrange and write it as equal to 2 root E divided by root pi kt raised to the power 3 by 2 E raised to minus E by kt into dE. Okay. And now, we can look how this molecular velocity, that means maximal distribution of curve is affecting with different temperature, how the molecular kinetic energies, Maxwell distribution of molecular kinetic energies is varying with different temperatures. You can see over here, that is, as the temperature is increasing, the spectrum is becoming more broader, isn't it? That is, from the equation also we can see that it is proportional to the square root of E. Okay. That means, as the temperature is increasing, temperature and kinetic energy is inversely related in the equation. So, as the kinetic energy is increasing, the temperature as the temperature is increasing, the kinetic energy will have a broader spectrum than when compared with the lower temperature, for the case of a lower temperature. So, this actually means the relation of the distribution of kinetic energies with respect to different temperatures. Okay. So, summarizing this class, we have first understood the Maxwell's distribution of molecular velocities, its mathematical representations we have gone through, and its dependence on temperature and mass. We have also seen that as temperature increases, the fraction of molecules having higher velocity increases and the velocity distribution becomes broad, while mass increases, the reverse happens, that is, the fraction of molecules having higher velocity decreases and the velocity distribution becomes narrow. And the Maxwell distribution of velocities, we have shown the experimental verification by Stern's experiment, and also we have found the reason behind, the actual reason behind the Doppler broadening of spectral lines. Okay. And finally, we derived the Maxwell distribution of kinetic energy, which is shown here. So, with this I am concluding this session. We shall see in the next class the different types of molecular velocities, as I said, the most probable velocity, average velocity and root mean square velocity. So, thank you students.